Hello guys, Josh again, back here to explain some key concepts that you have to know in order to name different compounds, especially different complex ligand molecules. So it's very important that you understand you memorize the common ligand names, because if you don't memorize the common ligand names, then it's going to be impossible to actually name a molecule if they give you a question. And then the different rules to actually naming, and then explaining the prefixes, the Greek prefixes such as mono, di, bi, or I should say bis, and tris. So here I'm going to pull up a slide explaining the different common ligand names. So here are the list of the common ligands that you have to know, and you also have to know their charges. And it's very important that you know their charges, because if you don't, then naming them is going to be difficult, because you need to know how much of each molecule you're going to have, especially when you're trying to determine what the overall charge of the metal that you're using is. So first things first, let's look at the different anions and know that if you just have an anion inside the actual ligand complex, it's going to be called bromo or chloro, and it's very important that you don't get this confused with when you just have the anion by itself. So I'll explain that once we go back to the board of the differences between naming bromo and bromide, right? So when it's in the complex when it's actually in that complex with the transition metal, it's called bromo or chloro. When it's just the anion by itself outside the brackets, outside the complex ion, it becomes bromide and chloride. And then there are a couple other ones that are very important for you to know, like water. Like water is aqua, and it is a neutral molecule, so it has a charge of 0. Ammonia also has a charge of 0, carbon monoxide, and ethylene diamine, also abbreviated as EN. And when I go over the prefixes, I'll explain to you that if you have more than one molecule of EN, for instance, if you have 2 molecules of EN, then the prefix bis is used because there's already a prefix in the name. The di in ethylene diamine makes that is the reason why that you have to, instead of saying diethylene diamine, you say bis ethylene diamine. So anytime you see a prefix within the name of the molecule, you can't use the same general Greek prefixes such as mono or di or tri. You have to use bis, tris, tetrachus, pentachus, and the other prefixes. And then a couple other ones that you should know, like oxalate is -2, and then knowing the charges of a couple other molecules. Here's a list of the actual prefixes that you guys need to memorize. And most of you probably already have these memorized because you've come in contact with naming different compounds many of times. But, you know, for instance, you have mono, you have di, tri, tetra, penta, hexa, and so on and so forth. And then remembering that if you have that prefix within the name of a molecule, instead of di, you use bis. Instead of tri, you use tris. And then instead of tetra, you use tetrachus and pentachus, and so on and so forth. So it's very important that you just remember these prefixes and the way that they're used. And also remember that if you have 2 consecutive vowels together, you drop the vowel of the prefix. So if you have mono and oxide, you don't say monooxide, you say monoxide. So you drop the O in the mono part, and it just becomes monoxide. Or another case would be tetramine. It's just tetramine. You don't have the multiple vowels. So it's very important that you remember that rule as well. So transitioning back to the board. So as you can see here, this is the example that they want us to name. So they're going to give you a molecule like this. Sometimes it can be shorter, sometimes it could be longer. But the concept of understanding the rules still apply. So if you don't know how to determine oxidation states, go back to the video on oxidation states and learn those rules, because those rules are going to apply, as you can see over here. But first things first, they want us to name this molecule. So it's important that we distinguish what our cation is and what our anion is, right? So our cation is going to assume the positive charge. So we know chlorine is always going to be negative. Therefore, it's going to be our anion, making this whole complex is going to be our cation. right? Therefore, everything within this has to be named based on the rules for naming the cation, right? And when you're actually naming the entire molecule, you want to do cation and then anion. So you never name the anion first and then the cation. So notice here that we have a chlorine in our cation and a chlorine in our anion. But these two are not going to be named the same, which I'll explain later. But it's very important that you never name anion or and then cation. So another rule that you have to remember is that the metal in the ligand is always named last. So you never start off with your metal being named first. You list everything else off, and then you list the charge of the metal with the metal. So the method that I like to do is to list everything out first, and then explain, and then combine everything essentially. So here I know that we have 5 waters, right? And we know that 5 waters is going to translate to pent aqua, right? Because water is aqua. And then since we have 5 of them, we need pent, right? And remember how, moving on, then we know that we also have 1 chlorine. And since we only have 1 chlorine, we don't put monochlorine, it's just chloro, right? And this is different than this, right? Because here, when we have this chlorine here, it's chloro. But when we are going to name the chlorine on this side, since it's the anion and it's not a part of the ligand complex, it's not going to be chloro, it's going to be chloride. So that's the distinguishing you have to be able to do when you're actually naming this molecule. Then you have to figure out the charge of the actual metal. So the metal in this case is chromium, and we know that the overall charge of this ligand molecule is +2 because we have a charge of -1 here with chlorine, but since we have 2 of that, that's going to give us a total charge of -2. And then we know that the overall charge of this entire molecule is 0, so -2 plus something else has to equal 0. Therefore, the charge of this entire molecule is going to be +2. Using that same logic, +2 is equal to our unknown, which is X, the charge of the transition metal, X plus 0 minus 1, right? Because water has a charge of 0, and then chlorine has a charge of 1. And since there's only 1 chlorine, it's going to be +2 equals X plus 0 minus 1. Therefore, X has to equal +3, meaning that chromium is going to be 3 plus, or when you write it out, it's going to be chromium 3. So now we have everything that we need to name. So we know it's always cation, then anion. Because it's cation, then anion, our chloride is going to be named last, right? As you can see right there. So now we combine everything in alphabetical order, not taking into account the actual prefix. So in this case, if this is P and this is C, so you would think to name the chloro first, but you have to remember you're not taking into account the prefix. Therefore, it is pent aqua, right? Because this is the cation, and we said that the metal is always named last in that cation, right? Or in the ligand molecule. So we say pent aqua, chloro, chromium 3 chloride. So the next example I'm going to put up on the board is going to be following the same rules. All right, guys, so let's take another look at this example here. So here's another molecule that we're dealing with. And again, we know that the overall charge of this molecule is 0. Therefore, everything in here must equal a total of 0. So we know our cation in this case is potassium, right? Because potassium is going to assume the positive charge. And since we have 3 potassiums, the overall charge will be +3, making the overall charge of our anion -3. So the overall charge of this entire thing is going to be -3. Therefore, everything within the brackets has to sum up to be -3. So again, you have to understand how to determine the charge. So in this case, we have the charge of -3 is equal to X, our unknown metal, plus cyanide, which is also going to be -1. But since we have 6 cyanides, it's going to become -6. So -3 is equal to X plus -6. Therefore, X has to equal 3. And then iron, that makes it iron 3, right? But because we're naming it inside the ligand, iron changes to ferrate 3. So if you don't understand why this is the case, then you should look up the different metals that actually change states, or change names. So sometimes, most of the times, the metal will actually stay the same, but in some cases you're going to see, instead of it being iron 3, it's going to be ferrate 3, right? So now we know that we have 6 cyanides, and then we also have, or since we know we have 6 cyanides, it becomes hexacyano, right? And this is important that you make sure you go back a couple minutes ago if you forgot the name of cyanide in terms of how it's named inside the ligand complex of the ion. So now we can basically piece everything together because we know our cation, which is potassium, and now we know our anion, right? So we always name cation, then anion. So this becomes potassium. Because potassium is not a transition metal, there's no need to put a charge there. It's not potassium 1. It's just potassium, and then our anion is hexacyanoferrate 3. So this is another example of piecing all the different rules together to get you the correct name of the molecule. So I'm going to pull up this slide explaining the different summary questions that you can use to determine whether or not you actually understand these concepts. And if you get these questions right, then you can move on to the next video.